Hey everyone, welcome back to my channel. I'm sorry that I've taken ages to get these videos up. I just completely forgot about them and got distracted by my uni assignments. But I should hopefully have a couple coming up today. So firstly, we are looking at biopsychology. And before I get started, I want to do the usual. Please like and subscribe and share this with your friends. Like, I'm totally happy if you guys share this with your friends if you find it useful, because I know I've had a few people emailing me and just asking if it's okay for them to share, and I just want to say now, go ahead. I mainly make these videos just purely to help people. I started doing them to help myself when I was doing my A-levels, and I now do them to help other people, and I've had so many great comments off loads of people, so thank you so much. You will just have to excuse me today because I've got a bit of a cold, so my voice, I may have to cough a bit, or I might sound a bit groggy at times, but please excuse me for that. So firstly, looking at the different systems of the body. So firstly, you've got the nervous system, which is organised like the diagram below that I've sort of made. And I sort of like diagrams like this because I find it so much easier to sort of visually see how things work. So the central nervous system, which is on the left-hand side of the diagram, consists of the main parts of the body, the brain and the spinal cord, and controls the activity between them. Whereas the peripheral nervous system is in control of everything else basically. And then this is made up of the autonomic and somatic nervous systems. So the autonomic nervous system governs any automatic behaviour, so like our natural reflexes that we have. But then the somatic system controls the muscles and receives sensory information. And then obviously you've got the sympathetic and parasympathetic systems that are part of the endocrine system, which I'm about to talk about. So the endocrine system instructs glands to release hormones, which are chemical substances that target specific organs to do certain jobs. So the pituitary gland is the master gland of this system, and the sympathetic system prepares the body for fight or flight by releasing adrenaline from the adrenal medulla to dilate pupils and increase heart rate, etc. So basically, the moment you're about to get on a roller coaster at a park, this is what is starting to fire up your fight or flight. Is your body is releasing adrenaline from the adrenal medulla, and that is increasing your heart to increase its rate and sort of all the other things. And that's often why people tend to you will stop becoming hungry the moment you go onto a ride. So all your adrenaline stops your muscles from, or like your digestive system from doing anything to make sure to save as much energy to get away from this fearful situation. And then the parasympathetic system relaxes the body to rest and digest by stimulating digestion and decreasing the heart rate. So this is basically what happens once you've done the ride and you start to calm down. So looking at the neurons and synaptic transmission. So neurons, every type of neuron have a cell body, a nucleus and a dendrites, which is really important to note because I'm fairly sure there's something you need to know. You need to know what is common between all of them. And there are three main neurons. There's the sensory, relay and motor. So the sensory neurons carry messages between the peripheral and the central nervous systems. Relay neurons connect the sensory and motor neurons to transfer information, and then the motor neurons connect the central nervous system to effectors such as muscles. So sensory neurons the relay neurons are basically just in the middle of the sensory and motor, connecting them together and making sure the information is transferred. And then you've got the synaptic transmission, which is when neurotransmitters are chemicals that relay information. So neurotransmitters are chemicals that relay information across synapses. And so you'll start off at one neuron, it will start in an electrical form, and then the information will travel chemically across the synapse, and then once it gets to the next neuron, it will become electric again. So inhibitory neurotransmitters make a neuron more negative, so are less likely to fire, for example the serotonin, whereas excitatory neurotransmitters make a neuron more positive, so are more likely to fire, e.g. adrenaline. And here is a picture of like a synaptic transmission, sort of a synaptic gap. So you start off with the information is travelling down the axon, and then you've got the neurotransmitters in the synaptic vesicles, and then these are released over this gap, and in this gap, which is when they are chemical form, and then they are received by the postsynaptic receptor sites, and then carry on moving through the body to move this information forward. And obviously this seems like it'd be quite a slow process, but obviously from the viewpoint of how our body reacts to things, it's a fairly quick process. So moving on to the localization of function in the brain. So the localization of function is the belief that specific areas of the brain are associated with certain processes. For example, the idea that the left side of the brain is to do with like science and maths and numbers and stuff like that, and then the right hand side of the brain is to do with art and creativity. So firstly, you've got Broca's area, obviously founded by the lovely Broca, which is an area in the frontal lobe related to speech production. And Broca's aphasia describes when a person can understand language but cannot speak. I think this is pronounced Wernicke's area. So this is an area in the temporal lobe important for the comprehension of language. And Wernicke's aphasia is when a person can speak but not understand language. Therefore, Wernicke and Broca's areas are very much the opposite when they start to deteriorate. They've got the motor cortex, which is responsible for any voluntary motor movements. They've got somatosensory cortex, which processes input from sensory receptors in the body that are sensitive to touch. Strength of this is Tulving et al. Revealed that episodic and semantic memories reside in different areas of the prefrontal cortex. I will just mention that there is a spelling mistake in there. I'm sure many of you just noticed it. So it's actually spelled S-E-M-A-N-T-I-C. However, laterally states the extent of damage has an impact on the effect rather than its location. Plasticity and functional recovery. So plasticity is the brain's tendency to change and adapt as a result of experiences and new learning. For example, Maguire et al. Found taxi drivers had a large volume of grey matter in the hippocampus than average individuals, and was larger in those who had been taxi drivers for longer. And looking at functional recovery, this is a form of plasticity following actual damage via a trauma, and the brain redistributes functions to undamaged areas of the brain. Neuronal unmasking refers to dormant neurons becoming active. So in our brains, we have loads and loads of neurons that are just dormant, waiting to be used, and then the moment that a brain becomes damaged, they become active again, working to replace the neurons that have been damaged in the accident or the trauma. And then stem cells can also be used to replace brain cells. So these are made. So stem cells comes from sort of like bone marrow, which is often why you tend to see with cancer treatments that they'll get a bone marrow transplant to gain these stem cells, because these are basically base cells that can turn into any sort of cell that you want, if that makes sense. That's sort of the best explanation I could give. They're basically just base cells that can look at their environment and decide which cell is required in that environment. So they can turn into like white blood cells, red blood cells, platelets, that sort of stuff. However, it is important to note there can be negative plasticity, so it's not always useful. So obviously prolonged drug use can reduce cognitive function as a result of negative plasticity. Moving on to hemispheric lateralisation. This is the idea that two hemispheres of the brain are functionally different. Like I said earlier, the left controls language, and the left side of the brain controls language, but then controls the left side of the body, whereas the right side of the brain controls visual and motor tasks, and the left side of the body. And to look at this, individuals' brains were split by cutting the corpus callosum so that each hemisphere could not communicate electrically. This was done purely for people with epilepsy in the hope to try and stop their seizures. And then Sperry and Gaziniga conducted split brain studies using these individuals who went through this surgery by showing them stimuli on the left hemisphere of their brain and asking the participant to respond. They would do the same thing to the right hemisphere and get no response, as language resides in the left hemisphere, which was their formal conclusion from the study. So basically, to explain that, they would have a barrier in between like the left and right eye, I think it was, and then the person would be asked to do something. If they were using their left hand side of their body, it was testing the right hand side of their brain, and then if they're doing something with the right hand side of their body, it was testing the left side of their brain. They'd ask them to do something using their left hand side of their brain, they'd be able to do it perfectly. And then if they tried to do it with the right hemisphere of their brain, it would just not happen because they wouldn't be able to comprehend it. Obviously, a strength of this is the standardized procedures. However, is language really limited to the left-hand side? Because obviously, looking at the idea of plasticity, and it is also hard to generalise studies using split brain patients because we don't necessarily know the effects that cutting the corpus callosum had on the way their brain functions. There are multiple ways of investigating the brain. So firstly, you've got the fMRI, which is the functional magnet resonance imaging, which measures the changes in brain activity while doing a task. Of course, it's reliable because it's a scientific method, but it does ignore the communication between regions of the brain. You've got the EEG, which stands for electroencephalogram, which uses electrodes to measure electrical activity in the brain. This is useful in clinical diagnosis, but cannot look at specific brain regions. Because it's in a non-invasive procedure, it just puts little sticky bits on you. You can't necessarily see which area is doing what. You've got event-related potentials, which use electrodes to measure electrical brain activity when doing a task, which is useful for studying the effects of specific stimuli, such as the effect of music when you're doing revising, but it needs a lot of trials to gain good data, which is not always available. And then obviously post-mortem, so looking at the brain after a person has died, and this is where you actually look at the physical brain to find underlying pre-death issues, which has helped understand the origin of schizophrenia, so that is a real-world sort of application of it. However, there is confounding variables. Bodily rhythms. So firstly, you've got the circadian rhythms, which last about 24 hours, and this tends to be the more sort of common one. So examples of this are the sleep-wake cycle, body temperature, and hormones. But the sleep-wake cycle is also determined by daylight and temperature. And looking at the evaluation of this, you've got the real-world application, because obviously looking at the shift work, for example, for nurses and doctors. But there are individual differences. As it can be found, it can vary from 13 to 65 hours. You've got the ultradian rhythm, which lasts less than 24 hours. An example of this is the 5 sleep stages and the basic rest activity cycles, or BRAC. These can be studied using brain scans and sleep studies, but it does not explain insomnia. And then looking at infradian rhythms, these last longer than 24 hours, so the menstrual cycle and animal mating seasons. But the menstrual cycle can be affected by exogenous cues. Endogenous pacemakers and exogenous ligabers. So endogenous pacemakers are mechanisms within the body that govern the internal biological bodily rhythms. The suprachiasmatic nucleus is in the hypothalamus and receives information about light, so it can act as the master clock. It then passes this information to the pineal gland that controls melatonin. And then moving on to exogenous ligabers, these are environmental cues that help to regulate the biological clock, for example, light and social cues. And by social cues, I mean sort of, like every day you have dinner at 5 o'clock or something. Strengths for this are the animal studies. So they use a mutant hamster to demonstrate the suprachiasmatic nucleus. Now, off the top of my head, I can't remember the greatest details about this, as it has been like 2 years since. Yeah, 2 years since I did my psychology A level, so I can't remember the greatest details about this one, but I'm pretty sure this is where they removed the suprachiasmatic nucleus out of a hamster, and then it had a huge effect on its like mechanisms, its body rhythms. And then obviously there's human studies as well. So Burgess et al. Found that you can avoid jet lag with the presence of daylight. So basically, if you're going on a long flight, if you just spend a lot of time in bright light, in like daytime, just going out and about, then it will help avoid the effects of jet lag. Although obviously there are slight ethics to the animal studies that I mentioned, so is that really fair on the hamster to remove its suprachiasmatic nucleus?